Good afternoon, everybody. My name is Carlo Boursier. I'm a researcher at the Department of Mechanical and Aerospace Engineering at Politecnico Torino. And indeed, my talk is about the effects of heat treatments, post-processing heat treatments, on stretch-dominated lattice structures for improving, let's say, the energy absorption capability of these structures. So from a mechanical point of view, usually lattice structures are divided into those called as stretch-dominated, characterized by high stiffness and high strength, and so the found application where stiffness and strength are required, and those called as bending-dominated, which are instead characterized by a huge plateau of the stress, a huge amount of strain that can be accumulated, and that usually finds application into applications where energy absorption is instead required. So what we wanted to study here, what we wanted to investigate in this study, was that if we want to tune the structural response through heat treatments, so if we can convert a stretch-dominated structure into a bending-dominated one. And to do that, we started from a well-known stretch-dominated structure, an octet truss, made of aluminum, silicium, tin, magnesium alloy. We used specimens with 2x2 cell replications and 3x3 in the three directions. Then we applied the heat treatments, post-processing heat treatments. One at 200 degrees, applied for 4 hours, and one at 300 degrees. And then we compared these results to the as-built conditions. We characterized the material in terms of defect population, grain size, and the mechanical response in terms of tensile test, basically. And then we tested the lattice structure under compression, performing quasi-static compression and impact test. And from that, we identified the most suitable heat treatment for our, let's say, energy absorption application. And then through that, we also designed a crash absorber for an automotive application. So we started from the micro-CT scans that we performed through a micro-CT. For us, the equivalent diameter was the defect size parameter. And the first thing that we observed was that there was no significant variation of the defect size with the three heat treatments, as you can see in this figure. While looking at the shape of the defects, we saw that in the as-built and the 200 degrees heat treatment, we have very not sphere shapes, while at 300 degrees, we have more rounded defects. We are reporting the biggest defects that we identified in these three scanned specimens. So the heat treatment has an effect on the shape rather than on the size of the defects. Then moving to the grain size, we do an ABSD analysis in a plane that is perpendicular to the build direction. And what we observed was that basically the heat treatment affects the grain size, increasing it, basically. You see that in this figure on the right. So at 300 degrees, we have, on average, the biggest grain size. And also, we observed that here with these maps, these color maps, you can see the grain size that increases with the temperature, but also that there is a crystallographic reorientation of them. So all the grains assume more or less the same colors. That is, they have the same orientation. And this change in the grain size is in accordance with the more rounded shape that we've seen with the micro-CT, I would say. Then we move to the characterization of the mechanical properties, starting from the tensile test. And we performed this with a digital image correlation to acquire the strains, the strain field, so that we were able to see the whole area, tested area, the whole strain gauge area, But also, we were able to identify the strains in correspondence of the necking zone. And here reporting the results in terms of true stress and true strains, where the strain are computed indeed where we have the necking. You see that there is a significant difference between the three as built 200 degrees and 300 degrees treatments. Basically increasing the temperature, we have an increase of the ultimate strain and a consistent also decrease of the ultimate stress. Then we tested the lattice structures, starting from quasi-static compressions. We did these on both 2x2 and 3x3 specimens with the three heat treatments, I would say. And we acquired the collapsing mode during the test. And what we observed basically was that we, in the as-built and at 200 degrees, we still get a brittle failure, a stretch-dominated behavior of the structure. While at 300 degrees, we obtain a progressive collapse. And this is observable also there on the figure on the right, where you see that the as-built has the highest strength. The 200 degrees is a bit smaller. And then for the 300 degrees, we have this trend of peaks and valleys around oscillating around a mean value. Because we need a progressive collapse. So when a row of cells collapse, then we have a valley, and then the next one is starts collapsing, and so we have again another peak, and so on. And and also here we observe, I'm reporting the results in terms of stress and strains, because I'm comparing both the 3x3 and 2x2 specimens. And here we don't see any significant difference between the two. That means that there is no size effect at this scale, at least. Then we move to the impact test. We performed impact test at 4 meters per second and 8 meters per second, basically 14 and 28, more or less, kilometers per hour. We recorded the collapse through an high-speed camera, and we did the test only on the 3x3 specimens. And what we observed was that, again, the 300 degrees heat-treated specimens showed a very progressive collapse, even if we are in this dynamic case. And also, if you look here, I'm reporting the results of the 300 degrees. We have the quasi-static one here in green, and then the other test, the impact test, in the other color. And you see that there is an increase of the maximum force, basically. So this means that there is a slight strain rate dependency of the material. These results, however, shows that while the 200 degrees, at 200 degrees, we get basically still a brittle behavior. At 300 degrees, we can get instead a very progressive collapse and a bending-dominated behavior. So we identified the proper heat treatment for our application. And for the design, we start firstly replicating our test into a finite element environment using LS-DYNA in this case. We modeled the structure with 1D beam elements. We use the elastoplastic material load that we identified with the tensile test, adding also the strain rate dependency that we identified through the Koper-Simons model. And then we validated our finite element model by comparison with the experimental results. In the two figures on the top here, you see the comparison for the 2x2 and 3x3 specimens. Then for the strain rate dependency, what we did was we calibrate the model on one velocity, 4 meters per second, and then we checked that all the results were in agreement also on the other velocity. And so the agreement between the finite element model and the experimental results validated our model. So through that, we could afford the design of the crash box, the crash absorber, for an automotive application. We imagine to have a C-segment vehicle with 1,400 kilos that has to face an impact at 15 kilometers per hour. We imagine that all the energy of this impact must be absorbed by our crash absorber, by a single crash absorber. And we also retain the envelope and mass constraints. So we want that our crash absorber is smaller than the dimensions that are reported here, and the mass must be at least, let's say, smaller or equal of the mass that is reported here. And for that, we came out through some preliminary analysis to a crash absorber made in this way, where we have the strut diameter that varies linearly from the top to the bottom, passing from 0.8 to 1.4 millimeters. This allows to obtain basically a force intrusion curve that increases, but also presents very small oscillations, both in the force and also in the deceleration profile, which enhances basically the safety of this component. The structure also presents a very progressing and smooth collapse, as is shown here. And in terms of mass and envelope, we achieved that a reduction of 40% for the mass and 50% for the volume envelope. So that is very important if we consider the case of electrification or hybridization of vehicles, where more space must be devoted for the electric motors, basically. So to conclude, the treatment at 300 degrees is able to change the microstructure of the material, and this allows the enhancement of the crashworthiness and the energy absorption capabilities, allowing also to obtain a progressing and smooth failure. With the crash absorber that we have designed and as shown here, we have achieved a very consistent mass and envelope savings, okay, with respect to the standard structure that is usually adopted, that is shown in the figure. With this, I conclude, and I thank you for the attention.